sweatshirts. So we are now changing gears. We will mention gases. Of course, gases exist all the time. We're going to kind of move away from the properties of gases now and start thinking about, well, now we have, as of last class, a container that has liquid and gas. Well, we have to expand our knowledge a little bit. Now we have a new type of material that we have to deal with that has maybe different properties than the gas. Now, obviously, you guys know gases and liquids are very different in certain ways, but they're similar in others. And I want to explore kind of the world of gases and liquids and from the point of view of energy and thermodynamics that we had before. And this will allow us to come up with a set of tools that are so useful that we can just apply them everywhere in chemistry. We're kind of being able to start building a universal language. We have a physical language about entropy and energy, pressure, temperature, Boltzmann's equation. We have this language that applies to everything. Let's see if we can simplify some things and come up with some kind of standard tools that we can use to analyze chemistry as a whole. So we'll motivate ourselves with phase changes for the next couple of lectures because I think it's such a fascinating part of chemistry that often is unappreciated. So we'll spend a little bit of time on phase changes, and we'll use it as a motivation to talk about two concepts that are maybe near and dear to your heart. That's maybe not the right way to describe it. Let's say you're familiar with them. And that's enthalpy and Gibbs free energy. So that's kind of where we're going. And those will be such useful tools for us that we'll use them for the rest of the class. They will be our magic numbers, enthalpy and Gibbs free energy. So we have to understand, how do we get to enthalpy and how do we get to Gibbs free energy and what do they tell us? And that's where our target today is, because I think you having a material that goes through a phase change is a really, really good test bed for understanding enthalpy in particular. You guys probably remember back in the day that Gibbs free energy, G is H minus TS, right? Enthalpy minus temperature times the entropy. So if we understand entropy, we understand enthalpy, then we understand Gibbs free energy. So they just build off of each other. But we should focus on enthalpy and understand it, what it means, what it's telling us, what can we learn from it, and then go from there about phase changes. All right, that's going to require us to change our point of view a little bit today. Lately, we've been talking about isothermal boxing. But what we saw last class was that when we fix the temperature and we change, say, the density of the gas, right? We feed in gas and we watch the pressure. Right? Independent of temperature, something interesting happens. Right? The gas condenses into a liquid. And then in some sense is independent of the temperature. It's only a function of the pressure or the density. So we should think about a box that instead of being at constant temperature, we should fix that box to be at having the variable that's changing be constant. So constant pressure instead. How does a system evolve if we keep the pressure constant and then change, say, the temperature instead of the other way around? That's going to be much more useful for us because pressure is not a very good number for liquids. We saw that in the previous class when we looked at the pressure curves for CO2. And there's a region of the CO2 kind of space, if you will, where the liquid is condensing and the pressure is not changing. So in that region, pressure is completely worthless. It doesn't tell us anything. It's flat. Pressure is constant. Right? But obviously something very interesting is happening in that constant pressure region. There's the condensation, which is a new behavior. So we should instead start thinking about constant pressure boxes at constant pressure. And that's a container that you guys are very familiar with, whether you know it or not. So let's draw our picture for what I'm about to fall. The constant pressure box looks like. We can still fix temperature, and that's, of course, a very useful thing for us to do in chemistry. And so what we're going to do is kind of look at maybe with a tunable water bath, change the temperature, a hot bath. We're going to have it at constant pressure. What does that mean? Today we're going to look at constant pressure. The term for constant pressure is called isobaric. So like we have isothermal for constant temperature. Baric means pressure. Isobaric means same pressure. We're going to think about constant pressure constraints. Isobaric constraints in the system. And the way to design a isobaric system is very, very straightforward. We're going to have a water bath. Have a bit of lag on my screen. Sorry. You're lagging. Yep, and it crashed. Great. Good start already. Good start to the day. Good thing I didn't write that much. Okay. Constant pressure constraints. I'm not going to write constraints. I'm just going to write constant pressure, isobaric. All right. We'll start over again. We're going to have a water bath. And you can fix it to a constant temperature if you want. Doesn't have to be. You may find it convenient to fix the temperature. And inside of that water bath, we're going to fix a container of material. But instead of closing it, we're going to leave it open. We have a flask or some beaker or something like that. With our material in it. Right, it might have some gas. Right, and it also might have some liquid. I don't know. And this is at constant pressure because if any gas forms, it's going to crash again. Come on. Son of a bitch. Try one more time. All right, now I'm not going to write anything. If this water, if this, for instance, this liquid boils or and creates pressure, right? That pressure exchanges with the outside. Right? So we have gas flowing out, and you could say maybe we have air flowing in. Right? So we have an exchange of pressure. Right? Pressure is maintained at the conditions of the pressure of the environment, which of course is just one atmosphere. Over a laboratory. Okay, so if any gas builds up, right, we have some evaporation, for instance, of a liquid or condensation, right? The pressure is always constant. It's always one atmosphere. Okay, so it's just an open container. Right? This is just a normal old chemistry hot bath. Constant pressure. This is why we use enthalpy and Gibbs-free energy in chemistry so often, is because the environment in which these quantities are well defined, which is a constant pressure, is the kind of work that we do all the time. You're in synthetic methods, organic methods. So this is at constant pressure. So the system is always at the pressure, always experiences a constant pressure. So what we can now say is we can, just like we did before a long time ago, is we can write down a function for the energy of this box. We want to sit down and think about the energy. What's the total energy of our box or our container? And the total internal energy U. We don't know quite how it looks, but we know that it's a function of three variables, right? It's a function of n, right? Because there's n particles. It's a function of S, the entropy or the heat. And instead of volume or temperature, instead the other variable is pressure. Right, and if we can fix the temperature, with bath, right, and we have heat exchange, right, we have heat exchange with the bath, right, we can say then that the system has a temperature, right? And we could say that U is a function of N, P, and the T instead of entropy. Because entropy in an isothermal bath, right? Entropy and temperature are related to each other directly. And I'm just going to rewrite this so it's nice and ordered. P is in the bath. Okay, so this is often called by the biochemistry world and the materials world. This is what's called an NPT ensemble. Right, and that's an ensemble is just a material that's kept at constant temperature, pressure, and number. Now understand the way that I've written this a little bit. The function n may be changing. Okay. Right, because imagine now if this liquid evaporates some molecules, right, and you build up some gas. That gas is going to leave and get exchanged with gas from the outside, right? So if the gas inside the container that's being evaporated is different than the gas of the environment, then you're going to have some exchange between the materials, right? So n may be changing, but the total number of moles will be the constant, right? Because you can only have so many moles of material given a pressure in an environment, right? You're only going to have so many gas particles in here, but some of them may be a different gas, right? So the total number is conserved, but there may be exchange of different types of particles in and out of the container, right? You might get some air in there. If the system generates CO2, you might get some air, right? So there's some exchange, but in the end, you ultimately will have the same number of particles inside of there, regardless of the type of material. So we can do the exact same thing we did before. We can vary U and think about how the rest of the variable, how U changes with respect to the other variables. And so we can vary U to U plus du. All right, and just like before, we can write the total derivative of the function du as the partial derivative, of U with respect to n. At constant T and P times dn, plus the partial derivative of U with respect to P at constant T and n times dP. Plus, we could either write du dt or du ds, depending on which container we're in, at constant n and p dt. Right. I'm going to use temperature because I think it's easier to think about. But we could also write this just as a note. We could also write this as du ds at constant n and p times the change in entropy. Right, depending on which box. And again, we can give labels to these partial derivatives, just like we did with the isothermal box, where we got the chemical potential and the pressure and the entropy. And we have a similar idea here. We have these three derivatives, and each one is corresponding to a specific variable, some sort of response of the system. I'm going to go ahead and copy this over to this page so we have some space. Didn't copy everything. Right, so what are these variables? Well, we can relate them back to the same variables that we had in the other boxes, right? We had something like du dn in our original box when we were talking about entropy in a closed box about temperature. And that's the chemical potential. So this is still the chemical potential, which we label U or mu. Right, that will specify, for instance, let me go back just a slide. Right, that will specify how much energetic benefit or loss the system will give by, for instance, having some of these yellow molecules leave for air to come in. Right? If there's some bias, there's some preference for air to come in, then the chemical potential will direct the system to lower its energy by removing these atoms. That tells you something about the way that things are flowing in and out of the system. Right? We may want to think about the chemical potential, for instance, between the liquid and the gas, right? There may be some bias for the system to want to take the gas particles and make liquid, or to make the liquid and evaporate to make gas, right? To change the amount of moles you have in each layer across the interface. The chemical potential will control that. So we'll have to think about chemical potential when we want to think about whether something wants to evaporate or condense. So here's a useful place for us to use chemical potential. Now here's a new variable we haven't seen yet. This is the derivative of the energy with respect to pressure. Remember before we had the derivative of energy with respect to volume, which we defined as the negative pressure. So here we have du with respect to pressure, right? So now instead of the derivative of u with respect to v, which gives you p, we have the derivative of u with respect to p, and that gives you v by definition. So this right here is the volume, and it's at constant moles, so we should write it as per mole. So this is the molar volume. The volume tells you how much the system will change, or sorry, rather, the pressure will change depending on the molar volume. How much energy changes with respect to pressure is dependent on the volume of the system. So if the volume is very large, now let's think about if this makes sense. Okay, so what it's saying is that if you have a function that you're just changing pressure of your system as a function of u, you're measuring u as you change p. As you increase the pressure, the energy increases. And what's the rate at which it increases? It increases by the slope, which is the volume. And what does this show us? Well, this says if your volume is really large, you have a large volume and you fill in molecules, the energy changes a lot.
We're talking about the volume of the box as a whole,
Sure,
including
absolutely.
all of the liquid and the gas.
Yeah, absolutely. Yes, the volume that the liquid fills and the volume that the gas, right? If that's, imagine you have a big container and you want to change the pressure of that container by 1 bar, and then you have a really small container that you want to change the pressure by 1 bar. Which one takes more energy to change that pressure? Obviously the big one, right? And that's what this is saying. It's saying that the energy changes with pressure as a function of the volume, of the relative to the volume. So if you have a big system, it takes a lot of energy to change the pressure. Whereas if you have a little system, it doesn't. So that's all that's saying. You may find it very interesting. Maybe you've noticed that we said that du dv gives us pressure, which is the output, and then when we take the derivative of u with respect to that output, we get the input back. There's like a reciprocal rule between v and p, and that's actually a real effect. That's a real mathematical observation, that there's some reciprocality between p and v. Take the derivative with respect to one, you get the other, and then when you take the derivative of energy with respect to the other, you get the original. Go back and forth. That's a feature of thermodynamics that isn't super important in this class, but it's a real effect, part of the math. And finally, we're left with these two expressions. Like, again, it depends on which one we pick, but it's the same idea. This needs to be, oh, it's a constant. So let me just take this down, right? So if we have an isothermal box, we have du dt, a constant n, and constant p. This has a special name. It doesn't have a special name. This is minus the entropy. And du ds, a constant N and P, we've already defined that before. That's the temperature. The expressions are very similar to what we had before. We're just changing things around a little bit. We're swapping variables between T and S and P and V, but everything kind of, there's a reciprocal law. You swap the variables and you get the other one out. So P and V are intricately connected, T and S are intricately connected. In the sense, if you take the derivative energy with respect to one, you get the other. And that would be the same here. If you take a derivative U with respect to chemical potential, you get N, number of molecules. Because obviously it would take more energy to bias the system towards some path if you have more molecules that you have to bias versus not have. All right, but we can go a little further than this. This isn't all that helpful. Because one of the problems, and Angie's comment kind of tackles this, is that pressure and volume in some sense are not particularly well-defined quantities, especially pressure, for liquids. Liquids don't expand or contract very much. They have a density. That density is temperature dependent, but it's not really pressure dependent. Very hard to make water more compressed when it has a liquid. And so it's not the best variable, right? So it might be worth to think about how do we rephrase this in some sense to think about the change in energy if we get rid of the PV part. We're going to say that this doesn't matter too much. And the reason why it doesn't matter too much, one is because some of the material we're going to look at, pressure doesn't really matter. It's not compressible. And we don't really care so much about the pressure or the volume of the gas inside the cylinder because the pressure is constant. Pressure is not changing at all. And most of the time, we're not changing the volume either, right? Because we have a fixed container, right? A glass container. It's not really expanding or contracting. If you have questions, go ahead.
Well, what about the concentration? Is that?
Yes, it does. But what? So let's go back. Which one of these terms is going to change the concentration the most? My argument is that imagine you have a flask that's initially filled to an atmosphere, right? We're in an atmosphere of pressure, and you're filled to an atmosphere of CO2. So the pressure differential is the same. And you initially set it up so that the only gas in the flask is CO2. It's pure CO2. Will that always be the case?
Not if you leave it open.
Right. Eventually diffusion occurs and molecules exchange. It's the only thing that this system is going to do in that process, leaving it still and equilibrated, is some molecules are going to leave and be exchanged by air. So which part of the energy affects that? Is it the change in pressure? No. Is the pressure not changing? Is it change in temperature? No, it's not. It's the chemical potential. So this is the equilibrium process about the mass transfer of material in and out, which is the diffusion property. And that happens regardless of pressure, volume, or temperature.
Got it.
Now you're correct. Now here's the interesting point, right? What if, for instance, we make this with it closed, and the initial pressure inside is 2 bar, and then we open it, what happens?
The temperature, I mean, the pressure is gonna decrease because,
It has to equilibrate to the outside.
right,
And what's going to happen to the molecules inside?
they're gonna leave.
Right, they're going to flood out, right? So at high pressure, we initially have it sealed and then we pop it open immediately and let it irreversibly exchange. Two things are going to happen, right? One is that you have a large chemical potential. It's going to drive molecules out because it wants to get rid of that and equilibrate the pressure. So if you have 2 bar molecules in the flask, you have to get rid of half of them. But dUdP is also changing because the pressure is going from 2 to 1. And so you get a volume change or a density change of that gas as that gas escapes and goes from 2 bar to 1 bar. Because this is the volume per mole. So this is the amount of material, this is effectively the volume of the container divided by the number of moles. So what you're actually seeing is the volume's not really changing here. Well, what is changing is the number of moles in that as it escapes from 2 to 1 bar. You lose half your molecules, CO2 molecules in that flask. So your energy changes because of the chemical potential, which drives the gas in and out through diffusion and leaking. And you also get an energy change because you've taken a gas at 2 bar and expanded it to 1 bar. You get an energy change for that as well. All right, so the equilibration of pressure with the outside environment certainly involves PV work, compression and expansion. But if the system is already equilibrated to the outside pressure, these two terms are basically zero. They don't really matter so much. So what I'm going to do instead is say, well, let's think about the energy. What is the change in the energy of the system if I subtract off the pressure volume part? Say I have the total energy of the system, and then I want to get rid of the PV part. I just want to subtract it out. Whatever PV there is, I don't care about. Because P and V aren't really going to change the system. There might be some motion due to PV work, maybe some expansion, maybe some contraction. Of course, liquids do change in volume a little bit with temperature and pressure. Very, very small amount, but they do. And we'll see that today. But I want to think about how does the energy change when I just subtract out the PV part. I don't want to worry about it. I just want to think about the heat content of the system that isn't being used for pressure volume. That allows us to define a new function. So we have an open flask at constant P. And we can write a new energy function. Which we'll call H. I like to give it little squigglies. H. Which is a function of N, P, and T or S, whichever one you prefer. And we're going to define it to be the total energy of the system plus the energy generated from PV work. Right? I have a plus sign here. Sorry. This needs to be a negative sign. It's negative V. Is that right? No, it's not. U plus P. Right, so there's technically a negative sign here, so I'm adding it to get rid of it. Okay, it's a negative energy.
H is for enthalpy.
H is for enthalpy, yes. So this is called enthalpy. Why it's called H, I don't know. I really have no idea. Right, enthalpy. And we're going to see that at constant pressure and constant T, H measures the total heat of the system. All the heat energy involved. Let me show you that that's true. So again, the idea is I'm taking the total energy of my flask and I'm subtracting off the PV. There's a negative sign, so that's why it's a plus. It's a negative on the other side. Well, U is equal to minus PV. So U plus PV would be 0. We have a plus. I'm going to prove to you today, really quickly, with just some simple math, a little bit of calculus, that this definition is what enthalpy is. That it measures that the change in energy, let me write this, the change in enthalpy is the change in heat of the system. I'm going to put it on next page. Proof. Right. So what I'm going to think about is having a flask that I'm going to put some heat into. So I'm going to take my flask, and I'm going to measure its H and vary it by just a little bit. Right. I'm going to put a little bit of heat into the system. Maybe I'll take it out. It doesn't matter. Maybe the system takes a little heat in from the back. What happens to the system? Well, what we can first say, remember that we can use H as U plus PV. So what we can say is that H plus DH is equal to U plus DU, right? Maybe the U changes a little bit, right? And maybe the P changes and maybe the V changes a little. So when we change the enthalpy of the system, we put a little bit of heat in it. Some of it will go into the total internal energy of the system. Maybe the pressure will change a bit. Maybe the volume will change a bit. Some mixture of change. Right, I'm going to expand this all out. All right, we have some foiling to do on the right. We have H. We're going to foil. We have H plus DH is equal to U plus DU times PV plus PDV plus VDP plus DPDV. Okay, just foiling out that thing on the right. All right, I can rearrange this a little bit and write this as U plus PV plus DU plus PDV VDP plus DPDV. And now I can use right? Now I have on the right-hand side my enthalpy. U plus PV is the enthalpy, right? So I can bring it back in. And I can cancel it out from both sides. This is equal to H. So I can cancel the H from both sides. And I'm left with DH is equal to DU plus PDV plus VDP plus DPDV, which is this weird second derivative term. So what do we have so far? Well, we have that change in enthalpy includes the change in internal energy of the system, which for an ideal gas is just kinetic energy. The pressure and the volume may change a little bit. Pressure may change a little bit. And then we have this additional cross-coupling term where the value of the pressure may affect the value of the volume. They interact with each other because, again, they're related variables. We have this cross correlation. But remember, we have an assumption about enthalpy. We're at constant pressure. So we always have underlying this the isobaric assumption, which is that dP is 0, constant pressure. So we can get rid of some terms. We can get rid of this term, and we can get rid of this term. These do not change at constant pressure. Now what we can do is use our definition of total energy. By going back to Joule, by using Joule's approximation, Joule says that U is equal to the sum of the heat plus the work. Right? Remember we talked about how you can melt ice by putting the ice in a warm bath, or we could melt ice by stirring it and applying heat to it and applying work to it. So we can either melt the ice through work or heat, and it's the same thing. The total energy is just the sum of the two. And this means that du is equal to dq plus dw, the change in heat and change in work. And remember what work is. Work is orderly motion. And for a gas or a material, a chemical material, the work that a molecule does is press against the walls and change its volume. PdV is work. So this is actually equal to this thing right here is equal to minus work. This is the negative of work. This is the work the system does, right, by changing the pressure or changing the volume. And we have that du is equal to dq plus dw. This is minus dw. So we have dq plus dw minus dw. So the work goes away. And what we're left with then is that the change in enthalpy is just a change in heat. Tells you how heat flows in and out of a system during process, whether the heat comes in or the heat is released. Right? Enthalpy measures that at constant pressure. We don't have that luxury in isothermal conditions. The reason why we don't have that luxury in isothermal conditions is because any amount of work or heat the system generates is immediately consumed by the bath. So any heat that you create is just sucked out by the bath. So you have a net zero energy change. If any energy increases in the box, then the bath sucks it out, and vice versa. And so you can't really define enthalpy for a closed isothermal system because of the fact that that heat is just it's conserved, and any heat that's created in the box gets released, and any heat created by the bath is input into the box to maintain the temperature. But here we haven't made any assumptions about constant temperature. We've only made assumptions about constant pressure, which means that heat can absolutely leave the system and never to come back, and heat can enter the system never to leave, I guess. All right, so the enthalpy is unique in this constant pressure system because it gives us a measurement of how much heat a process pulls in, how much heat a process releases at constant pressure. So let's look at an example. Let's define a couple of words. I'll use them. Some simple definitions. Right, when we say that dH is greater than 0, this means that our flask is absorbing heat. Right, if it's not at constant temperature, we know what that means. That means that the temperature increases. Okay? And the term we call this is endothermic. So a process that brings heat in is endothermic. Endo means inwards, thermic means heat. Yeah, these are probably Gen Chem terms, but it's nice to define them in our context. If it's the other way, that means the system releases heat. Which means that dT is less than 0. And we call this exothermic. Right? So anytime you hear me hear those words, just remember that this means something about the end. Endothermic. All right, there's not really a term for things that are DH equals 0, things that are D-less. Well, that's not true. There is one. I take that back. This is sometimes called adiabatic, which means heat-free, heat change-free. Adiabatic processes are very interesting. Hopefully we'll have a chance to highlight that in their unique properties. You do a lot of really cool things with adiabatic processes. Okay. So let's look at a quick example. I actually want to look at, let's see. Which example do I want to do first? Well, let's do this one first. I want to look at not a phase change, but a chemical change that's similar to a phase change. I want to look at the reaction of calcium carbonate in its solid form. It has different forms of calcium carbonate. One of them is called calcite. I have a picture of calcite. This is one of the common calcium carbonate minerals. This is what makes the pretty stalactites and stalagmites in lime. This is what we call lime typically. That down if you've never heard of that. Lime. The stuff you find on cave walls and stuff. Right. You can convert this into a different form of calcium carbonate that's much prettier and much more interesting for a mineralogist. Which is called aragonite, named after the place it was discovered, the forest of Aragon in France, aragonite. And it's a particularly beautiful red crystal. I don't know if you guys know this, but Dr. Luzik's big into mineralogy. He likes. So what I'm interested in is the process of converting calcite, which forms naturally in the ground. Well, they both form naturally in the ground, but typically calcite forms first from water depositing, water erosion of rocks, and calcium, and under great pressure or heat can convert into aragonite, which you can find in rocks as well. And I'm interested in the heat that may be created or removed from this process. And not only that, how much of the heat is being used to change the dimensions of the crystal, right? Because we're going from calcite, which has a very specific chemical structure. Right? You can see, well, you can't see what the chemical structure is, but you can tell that they're very different chemically. One's red and fluoresces and gives you these beautiful crystals, and the other one gives you kind of messy, goopy stuff. Right? They're made of the same thing and the same formula. And so if you want to convert one to the other, we need to think about, well, what's the enthalpy of this change? But maybe what's also interesting is how much does PV work really matter? Right? Do we really need to consider whether the volume changes at all in a chemical process? Right? Because the assumption that we made with enthalpy is that we don't care about PV work. We're just going to throw it away in chemistry. PV doesn't matter. Let's just show that that's the case, right? Because these are two really hard solids, right? Crystals. They're not very compressible. They're even less compressible than liquid by orders and orders of magnitude. You have to exert a lot of energy to change the effective volume or the density of these materials. And typically for a solid, we write down one value for the density. It's not pressure dependent. Occasionally it's temperature dependent. Typically when you write down the density of diamond, you don't give it a temperature scale. You typically just write it down. It's just one number because it doesn't change as a function of the conditions. So when you go measure the densities of these, the density of calcite is 2.71 grams per milliliter. And the density of aragonite is slightly more dense, 2.93 grams per milliliter. And you can go and measure how much energy changes in the system when it goes from one material to the other. And you can find that in this system, that delta U, the total change in energy of this system in this conversion is about 210 kilojoules per mole. About 200 kilojoules per mole. Okay, and what I want to ask is, what is the value of delta H minus delta U? Right, what is that? Well, remember that H is U plus PV. So this is the pressure times the change in volume of this process, right? How much does the volume really change? How much volume work is being used to rearrange calcite into aragonite, right? Because you got to move those atoms around, right? You have to rearrange the system. There's different forces acting on it, right? How much energy is exerted for every incident unit energy that comes in to do this process? I have problems with the mouse. This is a really rough day for me. I'm sorry, guys. How much of it's actually, what percent of the energy is used to change the shape, if you will? Because what you have, there's two things you have to do to change this material, right? One is you have to break the bonds between the different calcium ions and stuff like that and reform a new lattice to form this one. They have different shapes. So you kind of have to break all the bonds of all the salts and reform them. And part of that is heat, right? Heat has to break the chemical bonds, but there's also a physical reorganization of the system, right? We've gone from 2.71 grams per milliliter, which is less dense than this. And so the system has compactified itself, denser. So the volume characteristics of the system have changed. How much energy does it really take compared to the total energy required? So if this number is really small, then we can neglect it. That's kind of the demonstration I want to show you, is that in the end, this P delta V is not significant. Okay, so how would we calculate this? I'm going to go ahead and start a new page so I have plenty of space. Well, we're just going to do it like before, right? And enthalpy is just like energy. When we calculate differences, we calculate the end point minus the beginning point. Right? Just like you do in thermodynamics and chemistry, the enthalpy of a reaction is the enthalpy of the products minus the enthalpy of the reactants. So we're going to take the enthalpy of aragonite and subtract it from the enthalpy of calcite. Products minus reactants. By definition, this is going to be the total energy of aragonite. I'm going to write that as A, plus P times the molar volume of A, minus the energy of calcite, plus the pressure of the system, times the volume, molar volume of calcite. Right, I'm going to make some rearrangements here. This is equal to UA minus UC minus PVA plus PVC. And then what I can do, right, this right here is delta U. This is just a change in the total energy. So we'll bring that to the other side.
Oh, wait, I don't think that makes sense.
Why?
Because if it's UA plus PVA minus UC plus PVC, then by putting the minus before the second term in your, it's like UA minus UC minus PVA minus PVC. So you're now subtracting.
Oh, thank you,
PVA.
thank you. Sorry, you're right. You're right. So this needs to be a plus. This needs to be a minus. Would you agree with that?
Yes.
Thank you. So what that means, yeah, that actually makes more sense, right? So that means that the difference in the total energy change versus the heat change is equal to just the difference of the pressure times the change in the molar volume, right? And again, that's exactly what I wrote previous, right? Delta H minus delta U is P times delta V. And that's exactly what you get when you did this math, right? So what the saying is that the difference between the heat generated by the system and the total energy change, all that's left is the work. Right? So that's all we're calculating, is the work done by the system to rearrange the atoms into its new shape. So how do we calculate this? Well, all we have to do now is calculate how does the molar volume change. Right? We don't need to worry about this anymore. For our left-hand side, we just need to calculate this, but we can do that by considering the definition of molar volume. Consider that V bar is the volume that the system fills divided by the moles in that volume. If I take 1 over the molar volume, I get the number of moles divided by the volume. That seems like density. Remember, density is mass over volume, right? So the inverse of the molar volume is like the molar density, right? It's how many moles you get per unit volume. So we can convert this into density very easily by converting by the molar mass. If we know the number of moles, we know the molar mass, we can calculate the mass. But what I can now say is
a row bar,
a row bar.
like a row with a bar on top of it. Density is row, right?
Yes, correct. Yeah, so exactly. So exactly. So that's what I was going to say is that you by doing that math, by converting from moles to molar mass and using the definition of density, the molar volume is equal to the molar mass of the system divided by the density. Right, so this is the molar mass. So I can put this math in. NP delta V, or sorry, delta H minus delta U, which is the energy created or destroyed or not used for things other than heat, is equal to the pressure of the system times the molar mass of the material divided by 1 over the density of aragonite minus 1 over the density of calcite. Okay, those are numbers we have. All right, it's easy to calculate the molar mass of calcium carbonate. You guys ever learn what the molar mass of calcium carbonate is by your head? It's a really easy number to remember. Does anyone know?
69.
No, it's not 69. It's not 420.
I was gonna ask that next.
It's 100.
Oh.
100 grams per mole.
0.00?
0.09.
Ah.
But pretty close. But close for 3-6 phase, 100 grams per mole. So it's a really easy one to remember. Right. So all we have to do is just plug and chug, right? We're going to do this at 1 bar. Right, because our cave typically is only at 1 bar. We have things in terms of milliliters and volume in terms of meters and stuff. We can't use bar. We need to convert bar into standard units of pressure, which is pascals. 1 bar is 10 to the 6 pascals. Pascal is a Newton, like the unit of the SI unit of force divided by meter squared by surface area. So when we're dealing with numbers that are in milliliters and liters, we need to make sure that our pressure is corresponding to those units as well. So we have conversion, and then we have the molar mass. Hundred point oh nine grams per mole. Right, and then we just plug and chug the densities from before. Aragonite is 2.93. And the other one is 2.71. This gives me that delta H minus delta U is minus 2.8 times 10 to the 5. And now what are my units here? Units are a little funky. The bars are gone. We have pascals. Here we have grams per centimeter cubed. I'll write that here.
I thought, oh,
And so our units are pascals times milliliters or centimeters cubed times mole. Right, that's a strange unit. Pressure times volume times mole. Well, remember that PV is an energy, has energy, right? Because H or U is equal to PV. So these all have the same units. So this should be some sort of energy per mole, right? But remember that energy is in SI units, joules. That's pascals times meters cubed. So we're off by a factor of conversion between centimeters and meters. And so when we convert for that, we get that the difference is 0.28 joules per mole, negative. Okay, so the system, in order to convert calcite to aragonite, the system has to lose 0.28 joules a mole of energy. Actually, that's the gate. Work is negative, so this is positive. And that means that the system has to, right? Remember, the atoms before are less dense than aragonite, right? So the atoms have to compress to increase the density. So the system has to use some of that heat to compress. And the amount of heat that it uses to compress is exactly just under a third of a joule a mole. Now, how much did I say the total energy change of the system was? The total energy change of this, did I write it down? Yeah. Is 200 joules per mole. So of that 200 joules per mole, only a third of the joule is used for PV work. The rest of it is just heat. So when it comes to condensed phase chemistry, things that don't compress or expand very much, that are very hard, or like liquids where they're just kind of incompressible, PV work does not matter. It's a minuscule amount of energy. It's something like, what is that, 0.28 out of point? Yeah, that's a factor of 1,000, right? 0.1% of the energy is used to compress the atoms into the new shape. The rest of it is just heat. It's just heat. What that means is that we don't have to worry about PV work with most chemical processes. PV is so minusculely small that almost all of the energy required to do a process is just pure heat. So I'll write that here. Conclusions from the next page. Right. That P delta V, the delta H minus delta U, is equal to minus 0.28 joules per mole, which is like 0.1% of total energy required for process. So we can, for condensed matter, we can neglect PV work. Here. why enthalpy is so useful. Enthalpy measures heat, and by and large, the energy that chemical processes either absorb or release is heat. Heat is what drives chemistry more than anything. Because with things that don't move their pressure or their volume very much, you can just neglect that. Why don't I show you one last really simple calculation? I want to look at an example, a chemical process where PV work matters. There is an exception to this rule, and it's a small one, but it's maybe one that you can appreciate just from experience. So now consider the following reaction. You take 2 moles of hydrogen and 1 mole of oxygen and react them together to form 2 liquid moles of water. This is the opposite of what's called the water splitting reaction. One of the things, so what this reaction is what happens in the hydrogen fuel cell car. There's not that many of those in existence. It's kind of a hype thing back in the 2010s, and people didn't really pick it up because giving hydrogen is expensive and dangerous. But this is how a hydrogen fuel cell car works. If you have a compressed tank of hydrogen, the intake of your car, the front of your car, sucks in the oxygen like a normal car. They're combined. There's a spark. The H2 and the O2 combine and generate a ton of energy, and out comes just water. It's a really great. This is a great way to make energy because your output is water. Like no CO2, no NO2, none of that junk that internal combustion gives you. This is a reaction that's exothermic that only gives you water, which is why it's so appealing. And actually, people look at the other one too, the opposite, which is called the water splitting reaction. Because we have tons of this, plentiful resource we have. It'd be nice to have some more of this in our atmosphere. And it would really be nice to find a place to create this without having to use hydrocarbons. Because where we get hydrogen on Earth, where we get most of our hydrogen, like pure hydrogen, is by the byproducts of cracking hydrocarbons, oil. We get it from natural gas. Natural gas, you blow the natural gas up, right? And you want to remove all the hydrogen from it, get released hydrogen through cracking, and that hydrogen is taken away and purified and then sold as a product. Our major hydrogen sources from combustion or from oil. So this would be a nice way to make H2 if you just use water, right? The opposite direction. So let's look at ask the same question. What is delta H minus delta U, or P delta V? Right. Well, we can make a simplification here. We have gases on the left-hand side. Right. So we can use PV equals nRT. Right. We can use another formula if we want, but let's just use Pivner here. So we're going from a material that has a relationship between its pressure, volume, and temperature to one that doesn't really have that relationship anymore. Right. So what we can say is that delta H minus delta U is equal to the change in nRT. Now, what is changing in this reaction on the right-hand side? Well, R is not changing the number. T is constant, assuming constant temperature here. So what's changing is N, right? What have we gone from? Well, we've gone from a system of 3 moles of gas to one that has 0 moles of gas. Right, so we can write this as delta N RT, right? And so that's the change in the amount of moles of gas, right? We're assuming again that Pivner, right, PV on the right side, the liquid is 0. We don't care about it. And so any change in PV is going to be due to the fact that we're losing these gases. And so the total work change is the work required to change the pressure and volume to remove those 3 moles of gases. And so that means that this is equal to 3 RT. Approximately. And so at 298 Kelvin, delta H minus delta U is equal to 3 times 8.314, 298.15 Kelvin. This is approximately 75 kilojoules per mole. It's a minus sign because we lose 3 of them. Minus. So what that means is that however much heat the system releases, how much of the energy change, we can still calculate that. Yeah, I have that it takes 7 point. Oh, sorry, I'm off by a fact. 7.5. Sorry. Take 7.5 kilojoules per mole to adjust the fact that you're going from a gas to a liquid, right? So the PV is changing a lot, and it's a large fraction of the total enthalpy. We can calculate the enthalpy. We'll look at this more clearly next lecture on Tuesday. We'll look at how we calculate enthalpies precisely. The enthalpy of this system is equal to 2 times the enthalpy of water. Right here. We'll go through this math next class in case you're not clear exactly what's going on at the moment. The enthalpy of water is minus 285.9 kilojoules per mole. And we're going to subtract from it the sum of the enthalpy of H2, which is 0, plus the enthalpy of oxygen, which is 0. So the total enthalpy of this reaction is 2 times minus 285. That's roughly 600. What is that? Let's go ahead and count. That's roughly minus 5. That's minus 572 kilojoules. Okay, so what this is saying is that this reaction, as I said, is exothermic, right? We use this to power our hydrogen fuel cell cars or our hydrogen fuel cell, whatever you use hydrogen fuel cells for. Right, so it's exothermic. It releases 570 kilojoules of energy per mole. That's actually a really good number, really quite competitive with internal combustion, as we'll see. But the fraction of that energy that's being used to change the pressure and volume is a significant fraction. Right, it's a little over 2%. Right, now, that's not a significant fraction, I guess, compared to some fractions. But compared to the previous one, right, for solids, the total energy used. Yeah, that's right. Right. So 2% of the energy is used to change the physical shape of the material from gas to liquid here. And that's orders of magnitude larger than it is used for the solids, right? So if we were going to create some process that uses this hydrogen fuel cell reaction to power something, right? We could go and calculate the enthalpy and say this system is going to give us 572 kilojoules per mole. But in fact, we'd be off by 8 kilojoules per mole because we didn't account for the fact that it takes energy or releases energy to convert 3 moles of gas into liquid, that PV work. And so you would be off by 2 or 3% in your analysis of the energy created from your process because you haven't accounted for PV. So that's a small amount. It's not a huge difference, but again, we're talking about things at industrial scales where 2% can be huge, absolutely massive. It can cost you millions and millions of dollars. And we'll certainly talk about that when we get to equilibrium and start talking about different types of industrial processes that use chemical equilibrium. Being off by 1% or 2% in energy can mean the difference between environmental sustainability and no environmental stability and sustainability. These are kind of the differences that we're dealing with. So PV work constitutes about 2% of the total energy required. Energy release. Right. What that means also is that if you expect your system to release some amount of energy, like you're doing this reaction and you want your car to have so much energy to use, you're still off by 2%, right? You're going to get 2% less than you expect because 2% of that energy the system creates is used to rearrange the molecules. And that's energy you can't use anymore. That's not heat being released to the system. That's energy being expended to establish thermal equilibrium and to complete your process. You can't do anything about it. So gas phase reactions in particular, places where the volume and the densities are changing dramatically, it's very important to consider both the physical work that the system does, meaning pressure and volume changes, and the heat that the system either absorbs or releases. And so when you're dealing with internal combustion, other types of gas phase processes, they have to balance both of these things. Because especially in gas phase processes, if you're compressing your gas, like in a diesel engine, for instance, the diesel engine, you have to drive the compression stage by the release energy when you combust your gas, and that energy is then used to compress the gas in the next stroke. And so not all of the energy being released from the diesel combustion is being used to power the wheels. It's also being used to drive the piston up and down and compress the gas, and that requires energy as well. Right? So you end up losing some efficiency in a diesel engine in particular because some of the energy that you gain from expansion and combustion is then used to recompress the gas in the next step. So these are the kinds of balances that a industrial chemist or a process chemist will have to worry about. So it's very fine balance between different energies. Okay, but enthalpy in particular gives us a really, really nice number, allow us to measure at the very least the heat. So what we'll talk about next class is how the hell do we measure the enthalpy, right? So that's the next task, all right? So we'll look at that next class. We'll define what enthalpies mean. We'll talk about the international standard for enthalpies, and we'll do some calculations and look at some pictures. All right, have a nice weekend, guys.
You too.
Sorry for the late start. Wow, everyone left quickly. Oh shit.